Okay, we will restart. Thank you again to be here. We already started the lecture, even though I didn't start recording. Today, I will reconsider the manuscripts of last time, exactly from the beginning, because, okay, now I see. We concluded last time after defining our goals. And just shortly, I told you about the Lyapunov theorem, the second Lyapunov theorem. Let me say, in our numeration is the second one. We have seen the first one, which consists of, do you remember, of the, after calculating the equilibrium points of the system, consists of the possibility to classify if the points are stable or not. Okay, let me reconsider this now. Today we will conclude, in any case, the most important thing, and then we will see if we can meet next time, next week. It's not mandatory, of course. In general, what I would like to tell you next week, I can tell you directly when you decide, if you decide to work with Lotka-Volterra, we can discuss about the lecture on next time. We have a paper in the context of Lotka-Volterra in which we estimate the coefficient alpha, beta, gamma, delta. It is the lecture of next time eventually. And using this method to identify the parameter alpha, beta, gamma, delta, from a set of data of the mark of Coca-Cola, Pepsi-Cola, we were able, with a student of this course, we have in a paper also published, to establish what is the prey, what is the predators in the mark on related to Coca-Cola, Pepsi-Cola. We obtained the publication. One of these two companies tried to contact us, to contact IEEE, to withdraw the paper. Yeah, we have some problems. But IEEE decided the paper is still published, it's still there. Of course, we clarify at the end. I would like to tell you about this paper, but it's connected with eventually with the problem of estimation or alpha, beta, gamma, delta. You remember at the beginning of the course, I told you a lot about estimation, Do you remember why this problem here? Because X and Y, they are two, let me say, similar or specular dynamics, depend on the sign of the coefficient in order to establish who is the prey, who is the predator. It's just the coefficients, the sign. And if you have data, we can see what is the prey, what is the predators. But it is not in a moral judgment. It's just in a classification. Because the prey needs the predators and vice versa. This means Pepsi-Cola needs Coca-Cola, but Coca-Cola needs Pepsi-Cola. We elaborate just data. Ask me.
Which was the predator?
I cannot say. I can send you the paper because if I say, it could be that in YouTube some people from Pepsi-Cola and then they can attack me. I remember that it was not easy for us, but the third person, IEEE, clarified that this is an analysis, a scientific analysis. I would like nevertheless to ask, depends on the period. The data was over time, but believe me, we didn't, it's also prey-predator. It seems to us that they have an immoral meaning. Predator needs prey needs predators. You remember this equilibrium points. And a good mark, what is the good mark? With rules, allow to everybody to survive. with the good controller. Now we will see what is the good controller. A good controller should respect also the people who cannot be vaccinated. I will. The concept of the control is extremely important in the life because we can find trade-off. I have a course in master optimization control, optimal control. Also in our society, why we have laws. In fact, also in control, we say control laws and control law to regulate. Regulation could be also considered as in a word which belong to different fields, regulations to control the situation. Not necessarily to be predators. It's better or worse than to be prey. Remember, last time, colloquially, I tried to show you this equilibrium. But we will see today with simulation. Please.
This makes more sense in an ecological sense, where we have the rabbits and foxes, and if there are no foxes, then the rabbits overpopulate and stuff like this. But in an economical sense, I think it's not that obvious because you're like a startup and you have your component.
Yeah, I can understand. USA, to this interrupt you, then you can continue. Does economical fields or economical aspects is more oriented to the competition?
Yeah, exactly. As a business or startup whatsoever, you would want to succeed or to competitive. No?
I would. What you say is reflects the capitalistic economic world. Reflect this. But also in the capitalismos, there is different form from a capitalismos in this sense. In a farm for liberismos, yes, if you don't have, or if you have a few rules, but if the mark is regulated, this is also my opinion of the society. The idea is to give the possibility to everybody to survive. I mean, we cannot be happy alone. Excuse me if I would like to conclude this part with an ethic consideration. We cannot happy alone. We can happy just all together. The goal is not to, my opinion, that's a problem in the political position, which is based that we cannot have to be happy alone. This means the society, also in the context of, but probably you know better than me because you study economics probably, no? I think is a not willed economical world give the possibility to everybody to find a place. This means not liberismus, liberty by the sense to be regulation. I don't know, I'm not expert. Let me look at what I know a little bit better, control, in the sense of technical meaning. Thank you, nevertheless, for your contribution. We can work, if you want, together on this in the project. Why not? We have a literature. Which kind of control can guarantee that more protagonists in the market can survive? Anyway, prey-predators, the idea of the rule to both or more than compartment should survive. Okay, I don't know if of course I share. Okay, do you remember this? This was the Lotka-Volterra equation, which I already presented with the presentation, the presentation, let me say. But I added here two possible inputs. If this is the dynamics of the rabbits, and this is the dynamic of the foxes, this could be a possible input, for instance, food for the rabbits. Here could be food for the foxes. We can demonstrate that if the foxes have more food, they are less aggressive mathematically with respect to the dynamics of the number, the dynamics of the foxes. Could be interesting to think about what happens, what is this input in terms of Coca-Cola, Pepsi-Cola? What could be the input? Help from the government. You are more expert than me. When a company having a crisis, problems, here in Europe, in America is different. In Europe, the government try to help. It depends, but I'm not expert, but it happens. No? It's Volkswagen is in a crisis, in a social problem. I think this government try to help, an input. And this means to re-establish the concurrence without, I'm not expert. This could be an interesting thing. Also in this context, if you think that this can help you in the complementary context, no? That's something which you didn't see before. I'm sure that in this mathematical form you didn't see before. Could be interesting. We look at the beginning in the literature, and we can apply in our context. I'm sure that we will find something. Ask me.
Think about these Coca-Cola example.
I give you the paper. Believe me, I give you the paper.
Like companies get very large, there tends to be like higher regulation on them, which makes it more difficult for the firm internally to do some reporting because they get inefficient because they get so large. And then they have to give up market share again, and this is beneficial for other companies. So in my intuition, it makes sense that these Slot-Gabatera rules apply to markets. Because the companies at a very high level, there's a lot of inefficiency, a lot of regulation, high taxes, maybe if they have a high profit. So they like decelerate again, where this gives like open markets for other companies to rise. Also maybe it's because if we assume that competition makes risks more efficient, then it would mean that there are only foxes that will have a monopoly and they would get less efficient because they eat their own competition. Maybe that's the time.
Believe me, we produce some papers in this context, not directly on the competition, but if you want to consider these kind of problems in our examination of the project, I'm able to discuss with you, even though I'm not competent. This means you can ask me about the differential equation. We will see now the context of the controller, what we can do. But about the assumptions, about the mark, I don't have an idea. I trust you, definitively. Okay. Last time we have seen how we can modify this basic structure, Lotka-Volterra, with input here, to attain a very famous model. The name is SIR model. With the name came from the notation. S is the susceptible people, which represent here the prey. We can see that the dynamics is slightly changed with respect to this one. Basically, we put alpha equals 0. Alpha, I don't know if you remember, alpha was the GRU rate, I think, no? Something like that. It's as if we consider that the system is closed, basically the susceptible people does not increase. Meaning, of course, if yesterday 10 children born, it's clear that this is not as equal. But we can restart the software, the simulation. We will see what I intend with the new initial data. This means I will consider day by day, you remember the limit of my model, the simulation. Why that? Because I need, if today in the morning I receive how many people are considered susceptible, this means they include also the people who's born during the night, I have to produce a result, the result is UV, basically UV is the number of people which must be vaccinated. Is our input. This here was my general input in order to obtain a level of immunity, which I will redefine today in a few minutes. This means I am considering alpha equals 0 because I am considering constant during the time which I will simulate in the time I simulate during this day, because I receive the information about initial S, a initial R, a initial R today in the morning. The state is SIR, in which, as I already told you, is the susceptible people, which reflects the prey. I is the infected people. The dynamics is exactly the same. We can see here, no? With respect to the dynamics of the prey, which I presented originally, without inputs. And inputs here, do you remember last time I told you, if this input represents the vaccination, which changes in negative form in the sense reduce the derivative. This means reduce the number of people which can be susceptible. Here, we can consider an input as the quarantine, which in this sense acts on the dynamics of the infected. Let me see. Yeah, this was what I told you last time about SIR. Yeah, R is the recovered, which here in this model here collected the people who died and the people who basically was infected. Because once the people is infected in this model, we can assume that cannot be reinfected in the sense. But of course, it's a relatively simplified model, frugal model in the sense, but it's used. Let me see if I forgot to say something, but let me go ahead. We have another variation which we consider the latencies. It's a little bit more complicated, but we have also more complicated model if you consider that different compartments, something like people who can be reinfected. If you consider this more complex form in the sense, this means recovered, we will appear also in the susceptible, But anyway, let me go ahead with this because nevertheless is simplified but not so easy. R is the infection rate, excuse me. A is the move rate of infected. The unit is 1 divided time, because everything is, the unit is 1 divided time. This means number of people, dimensionless divided time is my input. Here is again number of susceptible people divided time. Let me see what I can. Yeah, again, if you consider here, it could be nice if you do it. The quarantine minus UQ, because in this sense, if you isolate the infected, the idea is the infected will be not, let me say, in the society, not this is what is present in the society, will be not present ideally. But of course, at this moment, I will present this one because if I include the UQ is too easy. Because we have two actions or the two inputs, and then of course we can control better the system. This could be a nice project together in order to analyze both and then to compare when's the result with UV, when's the result with UQ, the quarantine. The quarantine is the best, but of course it's difficult to be realized because if you don't have contact, somewhere the virus will extinguish. Okay, now we will conclude more or less here. You can see here that we can consider our goal, for instance, 0 infected people. Why not? This could be also an ideal situation, but could be also possible. Or we can consider minimal number of infected people. ID, desired infected. EI, excuse me, here, and EV, excuse me, EI could be this one and could be this one, depending. But let me consider 0. Why not? This is also realistic. What is interesting is the EV. No, ES, excuse me, I don't see without ES. ES, it's more interesting because it's the difference between the susceptible people and the desired people in the sense of susceptible. This means this SD is exactly the level of our immunity. We define the immunity of a society, consider this SD, which is the maximal number of susceptible people. This defined our immunity. This is not 0. Do you remember last time I discussed? This is not 0, it's never 0, because we cannot vaccinate everybody. Because in some cases, we have some people who, for medical reasons, cannot be vaccinated, or people for ethical reasons, I don't know what. I was not vaccinated for medical reasons. My family was totally vaccinated. Ideologically, I support the vaccination. Even though I have to say, and this is not my finding, that during the time, the virus will be weaker and weaker and weaker. But we know also from biology. And we can see also mathematically, because the goal of the virus is not to destroy the humanity, but to disseminate itself. Excuse me if I speak about the virus as in something which is thinking, but the nature is organized and they have a self-control system to survive for everybody. Because we need also prey as predators. Now, let me come back in my field, Lyapunov. You remember last time I told you about the first theorem of Lyapunov. We can see here the second theorem first, and the second is just our definition here, even though in some books is maintained this numeration. The second Lyapunov, the second theorem of Lyapunov says that in order to stabilize an equilibrium point, let me say a point, also an equilibrium point. Last time we have seen what equilibrium points are. No? Do you remember the derivative of the state equals 0? This means no changes in the S, no changes in I as an equilibrium point. This means the society, in terms of susceptible infected people, found its equilibrium. And today is 10 susceptible, 100 infected. Tomorrow is again 10 is susceptible. If susceptible, this means that our control system or our natural system, if we are satisfied with this, we don't have to do anything. In technical fields, this is quite important because I don't know if you know Segway. The Segway, you know Segway. We have 2 Segways in my lab. It's this problem here, to find an equilibrium point or to force an equilibrium point. When you push ahead, the system recognizes that should come back, because we have a controller, to an equilibrium point, but you have to force, and you run, because the system tried to find again its equilibrium point. Anyway, this is an asymptotically stable equilibrium point. This is an equilibrium point not stable, unstable, because if you move forward. But this is, we can work also in this field if you want. Let me come back here. We want to realize the equilibrium point characterized by S equal SD, our immunity. SD state the immunity. Again, the maximal number of susceptible people. I don't want more than this one. People which cannot be vaccinated. Makes sense, because we have to vaccinate a lot of people as much as possible. This means SD is the maximal number of susceptible people which we want to have in the society, together with I equals 0. This means our desired equilibrium point is in fact is 0, and S equal SD, not 0 SD, because we cannot vaccinate everybody. This means we have to estimate. No? This is not our goal, it's goal for other institutions. But we receive information about SD, what is suitable for our society. And typically, I, the infected, could be relatively small, also 0. Even though 0 sometimes could be a problem, but not now. In this problem, no. This is already clarified. Now, the theorem of Lyapunov, this theorem, says that I will be able, possibly, probably, to find the control law. This means how many people should be vaccinated per day, if considering this consideration, this sentence, this means the derivative with respect to the time of this function here. Now we will come back on this function, because I told you last time, but I would like to emphasize, is less than 0. Basically, this we have to find an UV such that this Lyapunov function, now we'll come back on this, will be negative over time. There is also something which I have to say, but it's easy. When, before doing the calculation, I will reanalyze this as last time. This function V is a function positive, is a function which is 0, I0, S equal SD, at exactly at the point, as I told you now, I equals 0 and S equal SD. Look, I equals 0, this part is 0, S equal SD is 0. What is this function here? It's in a paraboloid. Paraboloid, you understand what is? Let me draw the paraboloid. Basically, at I equals 0 and S equal SD, V 0. Did you agree? And it's always positive. This is the mathematical hypothesis of an Lyapunov function. What is the idea? If this is S of t and this is I of t, we have, if this is SD, we have a paraboloid, which is something like that. I don't know if you can understand that. It's 0, it's not very well done, for S equal SD and I equal 0. Meaning, roughly, it doesn't matter where I am for S and I, it doesn't matter. If I am able to find an U of t which realize this surface, I will fall down in I equals 0, S equal SD. Of course, it's quite colloquially. The demonstration and more consideration is more complicated. But think about the Lyapunov function in a positive function. Center in our equilibrium point, desired equilibrium point, should not be a natural equilibrium point. I didn't calculate for this, the natural equilibrium point. We can do. But we don't want. Could be also enough for you to have, to obtain, or to work in an equilibrium point. But in general, it's not in some kind of system, we need to put, to force an equilibrium point using UV. Do you remember in the COVID? Vaccination, quarantine. Because we didn't trust the natural equilibrium point. Because somewhere we will find, because do you remember the mutation of the virus is such that the virus will be weaker and weaker. Will never destroy the whole humanity, but a large part of it, believe me. I don't know if it's clear, because there is also some people who is immune. But some people that they have an immunitary system so strong that they will survive. But this is not the majority. Therefore, I am not against the vaccination. Please don't say that. Even though it's a position which must be respected, but we have to be careful, no? If this can damage the other population, anyway. And the second condition, which I didn't write, again, should be 0 at the equilibrium point, and should be 0 also the derivative of the equilibrium point. This means no changes also in this surface, but really extremely colloquially clarified. I didn't clarify anything, because to clarify, I have to show you the demonstration, the mathematical demonstration. We are not here in the complementary to go in depth, but intuitively we can understand that this is, if I am able to realize using a U, this kind of manifold. The manifold is a set of possible trajectories. Trajectory is the movement, the dynamics of S of t and I of t, trajectories, manifolds. Manifolds is a set of trajectory. If I'm able to vaccinate such that my phenomenon will move in this possible surface, I will converge here, definitively. And to do that, this should be our equilibrium point. And equilibrium means also that the V derivative, the variation of this function is 0. No? The derivative of this function is 0 at this point. But no? If I have a parabola, no? And the minimum, assuming that the minimum is 0, no? Or the our 0 is also the derivative 0, because we don't have variation. Now, this is a little bit a possible explanation of the idea of the Lyapunov, the second Lyapunov theorem. Let me show you the calculations. The idea is to calculate UV, which realize this manifold, these trajectories, this particular set in which I can see that the dynamics of the system will move. But please pay attention. This surface does not exist. In that sense, we want to move in a set which does not exist, but exists in terms of variation of S and I. What exists is the vaccination. What I have to do, better to say. And then exists S, exists I. I mean, it's the model. This is in the model. Look at this. If I do the derivative of this expression, again, you can ask me how I can choose this expression. That typically is a quadratic expression, is something which is always positive, and we can center very well in points, which defined our original problem, no? Or a goal, the original problem. The derivative of this function here, you are better than me in math, I'm sure, is this one, with respect to 1 divided to I squared, and with respect to 1 divided to S minus SD everything squared, is this one. I don't know if it's visible. Problem with the derivative? Gymnasium, no? Look, the derivative of this, 2 times I of the derivative with respect to t, the time. Because this is, I didn't clarify well. The system is in the dynamical systems. Everything changes over time. It's a shame, it should be nice if I have a time to show the demonstration, the mathematical demonstration, but it's boring, believe me. I think we can be happy with this, even though rough, but intuitively explanation. Everything changes over time. Therefore, I try to simulate a movement on this surface. Everything changes over time. EV is the vaccination per day, which realize this manifold. The manifold is an idea in the sense that doesn't exist as surface, but exists the value, corresponding value of S and I. No, the parabola does not exist, but you have X and Y, no? The correspondence. I hope that this course help you a little bit to associate to our mathematical knowledge something which can have a practical meaning. But during the project, believe me, this will be extremely emphasized. We can do also together per Zoom. Now, technically, did you agree that the derivative of this part is 2 times 1 divided to I multiply I derivative. Dot means derivative, also in your notation. Dot means derivative. Did you agree? Dot means the variable, the derivative of the variable with respect to the time. Dot with respect to the time. What is the derivative of this? 2 times 1 divided 2, s minus sd, because it's the derivative of up to 2, which multiply s derivative, because the derivative of sd is 0. It's no number. The immunity is the maximum number which we can accept as a susceptible people. The risk. No? Therefore, I justify this expression. Did you agree? Now, what about s dot? Why I'm considering s dot? Because s dot includes the input. This means, remember at the beginning I told you, I have to find a UV in the vaccination law, the vaccination policy. Each day I communicate how many people must be vaccinated in order to obtain SD. Yeah, if I consider S dot, we can see that UV is the present, a present. This means, in accordance to the Lyapunov theorem, which I didn't demonstrate, in accordance to this expression, if I replace here, if I plug in S dot, I will obtain this equation. Now we'll comment this equation, but it's easy to see. But in this equation, I am a UV. Oh, if I am a UV, in the equation of V dot, I can try to find an UV which guarantees that V dot is less than 0, because I can do something. Basically, the idea is the UV will change somehow the rates of this dynamics, or general the dynamics. Look, instead of S dot, I will write this expression. This means, and instead of I dot, I can put this expression. Both, I can plug in. But of course, this is extremely important to notice, as I told you at the beginning, that we have this. In any case, look at this. If I put this here, we can see that we will have these two terms. Because I dot is equal S multiply, excuse me, R multiply S multiply I. Therefore, we have this. Because I have to multiply by I. 2 and 2 will simplify. Why this one? Because I have to multiply I by this. This means minus A multiply I squared. I mean, we can justify these two elements just considering I derivative from the model. Because I derivative must respect the dynamics of the model. Then, if I put here S derivative, believe me, S derivative is easy. It's this here. I don't need to, excuse me. Let me close here something. Yeah, of course, I don't need to explain, because S derivative was exactly is minus R S multiply I minus the input UV. Now, from here, it's unclear what UV should be. For instance, now, if I say, for instance, this, if I say if something, if here, the question is, why this if? Yeah, here it's a shame, depends very often from experience, depends very often to look really very well which elements are important in this equation here. Sometimes it's not possible to find a solution. We will see in this case it's possible, but it happens that we have to change the cost, the Lyapunov function. But if I am not able to find a solution, this does not mean that the control law does not exist. Just means that I was not able to find 1. But it's enough to find 1. Look at this. Now we will clarify why this choice. If I consider UV exactly this equation here, we can see from here that the part of V dot is equal to 0. Which one? This. This means if I consider now UV equal this part, which I already clarified that allows to say that this element here or this part here is 0, plus, please pay attention here, an eta with eta positive. SGN, I clarify what this SGN is of S of t minus SD. Let me show you. As I told you, assuming that eta is positive, we obtain that this part here is negative. Now, let me discuss what I intended with this. Here, I have a possible explanation, but let me explain more mathematically. Again, if I consider this control law, UV equal this expression here I clarify why. I clarify the presence of this because using this element here, I can cancel, I can realize here 0. This means this part here is 0. As I told you, in a part of V derivative is 0. But 0 does not mean negative. Moreover, if this is negative, does not mean that V derivative is negative. But first of all, why this is negative? It's negative, even though it's not enough, because we have another part. It's negative. Why? Because if EV of t equals minus R S of t, I of t plus eta SGN, now I clarified what SGN is. SGN is this function. SGN of x. Basically, SGN of x is 1 if x is positive. This means if S of t is larger than SD, is 1. If S of t equal SD, we have 0. If S of t less than SD, we have a minus 1. I put x in general. Basically, I can write this sigmoid function. I don't know if you heard about this name, sigmoid function, because you can see here an S. Ideal S. Of course, can be also approximated by hyperbolic tangent. Very often we use the different function, but always sigmoid. Sigmoid, you understand? S. But let me consider this ideal function. In this case, x is S of t minus SD. No? Right? Now, why this is negative? It is written here. It is negative because if I plug in this expression here, I will obtain S of t minus SD, which multiply minus eta, let me write so, which multiply SGN of S of t minus SD, which is equal what? Minus eta absolute value of S of t minus SD. I don't know if you remember this. I mean, x multiply SGN of x equal absolute value of x. In math. If you don't remember, it does not matter. But this is always negative, eta is positive. But nevertheless, it's not enough. is not enough because I demonstrated that just a part of V is negative. Now, what I can do, I have to realize, again, from the rest of the part, for the rest, we have just this, you remember? Eta absolute value of our x is s of t minus st. If I am nevertheless able to demonstrate that this part, exactly what I try to explain now, is less than this one, or moreover, if this part is going to 0, I can say that V dot is negative considering this control law, which is our vaccination campaign, or a possible vaccination campaign. Probably not the best one, but a possible vaccination campaign. Again, if I am able to demonstrate that this part is less than this part, here, this part remains from this, which thanks to the control law is negative. If, again, this part is less than this, we will see that this part will be 0 under some conditions. V derivative is negative. This means in accordance with the Lyapunov theorem, this control law is a possible, probably not the unique one, is a possible control law which guarantees my immunity of my society, defined how I equals 0, and in particular, the immunity is S equal SD. The immunity is S equal S. But of course, we can also define a different form. Also consider different value of I. Okay. From here to here, what I did, I put in evidence I square. I square, which multiply these two elements minus this. I didn't change anything. I just rewrote everything in this form. Please, now I try to put some assumption. In case S of t is always less than A divided R. A divided R, do you remember? A was the remove rate of infected, and R was the infection rate. Please pay attention. If S of t, for each t, I didn't wrote, but I'm telling you, is always less than A divided R, then this is negative. We can see from here. Because if this element inside this parenthesis is negative, I squared is always positive. We have a negative. Here was negative because eta is positive. Eta is positive. Eta basically, what is eta? Look here. This function sign is dimensionless. This means eta is in a part of the people which must be vaccinated per day. This here minus this here. This is the full number of people vaccinated per day. Let me come back here. Okay, with this condition, I will obtain here. I commented that this condition is just a sufficient condition, but it's not necessary. You will see a little bit later, but we can understand it because in any case, if this is guaranteed, this is negative, but not necessary because, of course, I can compensate with the large eta. We can compensate with the large eta. Let me remain with this. let me consider now the equation, the original equation. I have just 1.5 slide, and then we simulate. And let me put here this. The control law candidate, the control law candidate. If I put here, I will cancel this part with this, excuse me, with this. And I will have minus eta, because of this minus, SG and ST minus ST. This means S derivative equals minus eta SGN of S of t minus ST. Now, if I do the integral of this part and the integral of this part, I will obtain this. You remember Ginnasio. You remember the integral of the derivative of a function is the function calculated at the extreme. You remember this? Easy, no? Clear for math. This means I have S of t minus S of 0 equals. Now, look at this expression here. Do you remember? This expression is 1 in case SGN is positive, is 0, excuse me, in case X, which in our case is S of tau minus SD, is positive. This means is if S of tau is larger than SD, is 0 if they are equal, is minus 1 if S tau is less than SD. But look, assuming that ST is larger than SD, why that? This is not conservative, this assumption. Conservative means restrictive. Because if S is less than SD, we don't have to do anything, because we already reached the immunity. This means the mathematical problem does not exist, because we are satisfied. We don't have to increase S. Less than SD, let me say even better. This means what we have to consider, this assumption here, which is not conservative. You understand the word conservative? It's not I mean, this assumption here could be also conservative. Now we will discuss, because probably it's not so general. Why should be that? Because it's comfortable, but if it's comfortable, probably cannot be guaranteed always. In fact, it's arbitrary. I don't know if the number of susceptible people is less than A divided R. This depends on the system, depends on the number of S. But this assumption here is not conservative, because if S of t is less than SD, the problem does not exist. I already reached the immunity, because I am under the SD. Ideally, SD equals 0, but I told you practically we don't do. Clear what is conservative, what is difficult. This is really the problem. If S of t is larger than SD. Now, math, this means if we have this, this means this is 1, the integral of 1 in d tau between 0 and t is this one. Because it's t, or better to say, minus eta t, because we have a minus eta here. This means S of t with this control law at this form here. This means we can see for a given initial value, which must be given every day, 0 is 8 a.m. in the morning, which I receive each day S0. How many people is susceptible, included how many people, as in children, were born during the night. Because as I told you, S don't have this, the rate, the reproducing rate, the grew rate is 0. This is the mathematical expression we can see here. But with this control law, S of t will decrease linearly. We can see from here. Starting from S0, I didn't put here, but it's clear, will reach my immunity at an infinite time And this time which I will reach the immunity, I called S star. Now we can calculate S star. It's easy to see because SD is known. If I want to calculate S star, S0 is known. Eta, I can choose. I mean, S star equal this one, clearly, math from gymnasium. This means if I want to reach S star very quickly, I have to consider very large eta. Do you remember? Eta is a part of the control law. It's clear that I have to vaccinate a lot of people if I want to reach the immunity in one day. But it's calculated. Better to say it's calculated here. If I want to have T star one day, eta is this one. In any case, T star at this expression here. In case I want to calculate eta, this is clear that if I want this is very small, eta will be very large. This means the people which I have to vaccinate must be per day. This is per day. I don't know if you remember from here. Number of people vaccinated per day. Everything is number for people vaccinated per day. This is dimensionless. This means it's the number of people vaccinated per day. In general, we have to consider both contributions, this and this one. But this I can calculate this. This is not active. This is active because eta I can calculate as the function of T star. T star, look at the picture, is the time in which I will want to reach the immunity which I fixed. Let me come back. You remember at the beginning, in one point I told you I would like to discuss a little bit this condition here, which is a sufficient condition, but not necessarily. I mean, let me come back on this condition here. It's sufficient because if this is respected, if this is less than this one, we have that's this. Let me. But this is negative. No? This is negative because eta is positive. Absolute value is positive. I squared is positive. This means if this holds, also V dot is holds negative in the sense. But let me discuss because what is the meaning of this? How conservative is this? And now we can say something more because you remember we obtain this equation or we discuss this equation. And let me see the last sentences. This means that S of t, this expression here, less than A divided R. I mean, I would like to discuss what is the goal for these last three calculations. How conservative is this? You remember, this is S of t. I told you now. This is our S of t, which I calculated considering the model and consider UV, which I propose. Please pay attention, which I propose. Because it's not the unique one. This expression here, considering this, becomes this. From this expression, look, we can write this expression here, which is interesting because, which is already I reconsidered here, because now we can see that in accordance with our control law, it's not necessary that let me say that's S of t less than A divided R for each t, because S of t is monotonically decreasing. Monotonically decreasing. This means it's enough. We can see mathematically too. That this must be satisfied. But in the worst case, it's necessary that this must be satisfied. Because if this is satisfied, then is also this satisfied. because I will add always something to this. This means S0 less than AR, it is enough to. It is enough. Now, think about at home, and now in this 15 minutes, I will simulate for you. Thinking, please, and this condition physically. With this particular control law, policy of vaccination, to guarantee that we'll achieve the immunity at time T star, which I can state, I can determine, calculate eta. How many people must be vaccinated per day together with minus R S of T and multiply I to obtain the stability. I mean, to obtain the immunity. For a given T star, I will obtain eta. Interesting this condition here. The initial value of the susceptible people must be less than this A. Again, A is the remove rate of infected, and R is the infected people. The rate, infection rate, the infection rate, to precise. Let me see if I can say something about that. It's clear, no, a little bit. Why it is clear? Think about if the infection rate is very small, this means the virus is not so aggressive, right? The infection rate is not so high. This means we have a contact, but probably nothing happened. Infection rate equal 1, each contact infected. For each contact, we have an effect. If it is very small for a given A, of course, this is not so restrictive. It could be very high, this S0. I don't know if it's clear to me. I can control the system very easy. This means S0 less than 1 million. Today we have 1 million, no problems, because the infection rate of this particular virus is not so high. We cannot vaccinate. This is a little bit colloquial to interpret what comes from math. Believe me, this kind of approach we will use. Let me fix this and let's move this. R is clear, the role in the denominator of R. Ask me if it's not clear. Anyway, smaller and smaller R, no problems, because we can see that this condition is not restrictive. It's enough less than 1 million. 1 million, no problem. We don't have this population. We don't have to do anything. For instance, the situation is not dangerous. If today I receive this data to verify, why A is in the numerator? It's in the numerator because if the A is the move rate of the infect, yeah, again, if this A is basically A, what represents the people we recover. You remember this? Or die. In this case, we didn't distinguish because the recover cannot be reinfected. It's a little bit strange what I say, but we can understand if this is very large. Of course, also in this sense, the virus is not so strong. Reflect somehow this reality. We can discuss from the project a lot of variations, also your suggestion to calculate R. Let me show you. You have 50 minutes for me, 5 past 8, to show the simulation and to upload the simulation. And then, of course, we can go deeper with the project. But let me show the simulation. 50 minutes. Yeah. It's so difficult with this math, but the idea is to show you how through math we can guess, we can have information about what happens in the society in case of such phenomena or phenomenon. But similar consideration can be done for economical system. Believe me. No? Also there we have two competitors. Here, again, the infected try to reduce the number of susceptible in this sense. Okay. Let me open MATLAB. It was hard, this lecture, a little bit, no? The language. Yeah, because I collected a little bit, yeah, control, nonlinear control, but the idea is to show you the idea. In any case, I have a working file. Based on this working file, we can realize different projects. And group worked also in the field fakes in internet on this project here. Inspired by a work from Virginia University, they extend this Lotka Volterra to recognize fakes from let me say normal information internet. But we can look now for the project if you want to go ahead with the Lotka Volterra a little bit together, more detail. Now let me show you the simulation, then we conclude. Okay, let me see if I find now Lotka. Okay, now. It's not here. Let me look where is Lotka. Probably is not here. I'm looking. Let me see. In the meantime, if I forgot to say something, in the meantime, the computer look for. But I don't think so. No. Oh, why didn't find? Okay, let me see where I can find. 1 second. Here, I'm sure that I will find. Yeah, found it. Let me copy in the right folder. I will show you. Yeah. Okay, let me copy here. I will upload at the end of the lecture. Let me share MATLAB and I will show you the simulations. Where is, yeah. Let me share. Let me do better. Okay, let me go to MATLAB now. I think you should see MATLAB. Okay, where is? Huh? I copied, where is? Okay, I copied outside, doesn't matter. Look, here we have some files which I will upload. Let me open these initial parameters. Upload, I mean, to call, to open, better to say. Today is quite slow, the computer. Why doesn't open? Okay, now. You can see here the parameter which I need clear all, from different course, from my course, but also from different topics. No? Oh, no, here is not exactly, I mean, the parameters are correct, but the comment is not right. This means, let me cancel here, no? Because probably the comment came from another. Yeah, in any case, alpha, beta, delta, gamma, we have seen this this parameter. I don't know if it is because here I see Kalman. Probably it's not this one. Let me open one, but I'm not sure if this is the right one, because with this SIR we did a lot of applications. I don't think so. Is this? I don't think so. Let me open, because I see this is Kalman. That is not exactly our control, because our control is sliding mode control. Let me see the file, but I don't think so. Is MATLAB is trying opening the file. Let me see. Ah. No, it's not this one. It's a shame. Let me look for another file. This is another application of the. Let me look again. There's another application. It's a shame. Ah. Let me look. Probably it's not here. Let me see if it's here. No. Why it doesn't find? Okay, okay, let me see. What I put here was SIR Kalman, huh? I have to find the material now. I'm not able to find now. No. Ha, it's not here. I would like to organize it. What do you think if we continue next week? You have time? So per Zoom? So I find the material, the simulation, and also I would like to tell you about the identification of parameters, also for per Zoom, if you are not here, of course. I am here nevertheless, because now I need time to find the material. This is the problem, because I have many, if you have time, we can stay in, but what do you think? In any case, I can do it per Zoom, per. So I am here. This means for me it's no problem to come. Yeah, of course. We can discuss today. Now we will conclude. Next week, in any case, I will have more time because to show the simulation, I don't need time. The most difficult thing is to find the simulation because you can see I find a lot of simulations, but with in different contexts, in context of observability, monitoring, but not control, but I have it. And nevertheless, I would like to tell you very quickly about the possibility to estimate this parameter alpha, beta, gamma, delta, which collapses in R and A in the somehow in our system. Okay, let me say so. Next week, half past more or less, I am here. You can nevertheless join per Zoom. I will communicate per my study or directly per YouTube. Concerning the project, of course, we can talk together now or next week we have more time because I don't need much time, believe me. The simulation typically, it seems to be more difficult than the theory, but it's not because it's just an implementation. Very often it's just to know where the blocks are. But again, in the project, I will give you working, if you want, working files. This means basically is to modify the files, or at least could be also this the exercise. Okay, let me close recording. We will see next week more or less half past here. If you are here, I am happy. If you cannot join me, if you cannot reach me in the lab here, per Zoom is always possible. Now, if you have time, if it's not too late, we can discuss project. Otherwise, next week we have time, nevertheless, because I will need not much time to show you simulation and to show you the method to identify the parameters, no, of the model. Thank you. Thank you.